Okay, welcome everyone. I'm excited to be here today for this tinyML UK talk. It's going to be an exciting one. We have Alasdair Allan from Raspberry Pi with us talking about the future. So the title for today's talk is Standing at the Edge, Looking into the Future. And before getting started with the actual talk, as usual, a brief introduction and then we'll dive in the talk right away. So let me just start by thanking all the sponsors that are sponsoring tinyML. You can see all the names here. There's quite a lot of them, and they're growing every time I present this slide. There's always a few more. So that's exciting. And I wanted to also thank the rest of the committee, the tinyML UK committee, that with me are organizing the talks, all the tinyML talks in the UK. And it's exciting because we've done quite a few interesting talks, and hopefully soon we'll be able to do an in-person talk, so stay tuned. One thing I want to say before diving into the talk today, a couple of things actually. First one is I'm looking forward to the tinyML Summit 2022 in March 28th to 30th of March in San Francisco. It's going to be at the Hyatt Regency. And we're also going to have the tinyML Research Symposium on that same week. So it's going to be March 28th at the same place. So this is exciting because there's going to be a lot to talk about, and it's going to be in person, and there's going to be a lot of people attending. And then tomorrow there is a talk. It's actually a hybrid talk, so in person and virtual, with Odin Shen from ARM. Talking about tinyML software and hardware. Without further ado, I'm going to introduce our speaker of today, Alasdair Allan. He's a scientist, author, hacker, maker, and journalist. He currently works for Raspberry Pi and is responsible for the documentation. In the past, he has worked as a consultant and journalist, focusing on open hardware, machine learning, big data, and emerging technologies, with expertise in programming, electronics, and especially wireless devices and distributed sensors networks. And I have to say that I've been admiring Alasdair's work for a while now. A lot of great articles in the last few years. And then, he's also a former astronomer. He built a peer-to-peer network of telescopes that acting autonomously, reactively scheduled observations of time-critical events. And interestingly, he's also contributed to detect one of the, I think what was the most distant object discovered at that time. So that's exciting. We'll hear more about that. We'll feel free to pop questions in the chat to know more. And with that, without further ado, Alasdair, the floor is yours. Welcome.
Thank you. So today I'm going to play the role of the king's fool. Anecdotally, at least, and there's at least some historic evidence to suggest it's just anecdote, the role of the fool was to tell the king things that they didn't want to hear, but everyone agreed that they should know. The fool, you see, having more leeway in such things than other courtiers. Hopefully this talk will leave you feeling uncomfortable and frustrated. And that's okay. I made you think. Because you see, the move to the edge and the machine learning models that are making it possible are giving us another chance to put computing out into the world in a way that makes sense. And we need to take that chance, because the next one might not come along for a good while yet. More than 10 years ago now, Mark Zuckerberg stood up and famously stated that the age of privacy was over, that privacy could no longer be considered a social norm. Zuckerberg sadly was proved correct, and this became the mantra of the big data age. And for the last 10 years, Silicon Valley really has pursued it with a vigor. But the companies we have entrusted with our data in exchange for our free services have not been particularly careful with it. This from Alan Kay in 1972, who anticipated the black rectangle of glass and brushed aluminium that lives in all of our pockets today, and the ubiquity of the ad blocking software we need to make the mobile web even a little bit usable. And yet, while Kay's prediction of the existence of the smartphone was almost prophetic, it was also in a way naive. Because Kay lived in a simpler time, without the ubiquitous panopticon. panopticon of the modern world, and without the security threats which arguably shapes the modern internet and our view of it. Because there really is only one business model on the internet today, and that's advertising. People have consistently refused to subscribe to services or pay for content. Instead, advertising supports the services that sit underneath almost everything we do on the internet. And behind advertising is the data that makes it possible. A series of almost accidental decisions and circumstances have led us to a world where most things on the internet appear to be free. It doesn't mean they are free, just that we pay for them in other ways. Our data and our attention are the currency we use to pay Google for our searches and Facebook for keeping in touch with our friends. And the Internet of Things, this big data-centric model has spread from the web to our things, and it hasn't gone well. For instance, 4 years ago now, it was discovered that the company behind Cloud Pets, essentially internet-connected teddy bears, had left the database exposed publicly to the internet without so much as a password to protect it. In the database were references to almost 2.2 million recordings of parents and their children. And with those references, you could retrieve the actual voice recordings directly from their Amazon S3 bucket, which was also shared without a password on the internet. The person that originally discovered this tried to contact Cloud Pets 3 times to warn them without response, and the database was only actually taken offline by a ransomware attack. So almost inevitably, the tide has turned. Just at the end of the before times, before the pandemic changed everything yet again in ways that are still somewhat difficult to predict, back in 2019, in fact, Zuckerberg stood up at the Facebook annual conference and said, "The future is private." This is an extraordinary statement. Even if you don't believe him, and let's face it, we really haven't been given any reason to, the idea that this man, the man that 10 years before stood up and sold us and the Valley on the mantra of the big data age, that privacy was no longer a social norm, said it, tells us something. It tells us that that age is over. Because move fast and break something shouldn't apply to our personal privacy or to our civilization. Connecting devices, building an Internet of Things has proved to be problematic. There are so many moving parts, not necessarily physical moving parts, but rather interactions. Every time software talks to hardware or other software, there's an attack surface, exploitable. For the most part, however, the wide-scale security compromises we have seen with the Internet of Things have been unsubtle. Mirai, for instance, was a piece of malware that identified vulnerable IoT devices using a common list of factory default usernames and passwords. It then logged into them and took them over to form part of a botnet. Infected devices continued to function perfectly normally, except for the occasional sluggishness and increased use of bandwidth. So their owners generally didn't notice that anything was wrong. Mirai started spreading back in 2016, and it's still around today, just not the threat it once was. But attacks are becoming more subtle. Attacks injecting mal-data, malicious data, and data spam are starting to appear. And I've seen at least one case where malicious data has been injected into a device network in the wild, causing real-world damage to real-world infrastructure. When you're building something, the question always has to be, what is it for? Why am I building it? And crucially, what are the outcomes I expect after I do that? Only then should you build the device. And we've seen a lot of unnecessarily connected devices where the data leaves the device and then unnecessarily makes its way to the cloud. And it's possible that machine learning on the edge could enable us to do away with most of these cloud connections, or in fact, make a lot of these connected smart devices smarter, unconnected devices. This is an actual screenshot from an actual application controlling actual smart light bulbs. Just like some US-based websites did, this particular light bulb app stopped their service when GDPR came into force in the European Union. You could still turn individual light bulbs on or off one at a time, but everything else was taken away if you told the app that you refused to accept their new privacy policy, which makes you wonder what data about when and what bulbs you were turning on or off is the company behind the app selling or using in ways you don't really expect. And to be clear, I'm not really sure this sort of response was legal under the GDPR. You can't refuse to provide a service just because the user refuses to let you have their data, unless the data is required to provide the service. And I can't conceive of a case where GDPR infringing data is necessary to turn light bulbs on or off. Can you? I think the very idea that hardware is just software wrapped in plastic has done real harm to the way we build smart devices. The way we talk to our hardware is an inherited artifact of how we write our software. The interfaces the hardware presents look like the software underneath, like software subroutines. We tell our things to turn on or off, up or down. We send commands to our devices, not requests. This works for now, as most of the current architectures for the Internet of Things seem to assume a human as part of the conversation within the system. We tap a button and the light goes on. We've taken a lazy route and decided that hardware, physical things, are just like software, but coated in plastic, and that really isn't the case. We need to move away from the concept of smart devices as subroutines and start imbuing them with agency. But the whole thing is sort of complicated by the fact that there aren't really very few actual smart devices in the wild. For most part, the current generation of smart devices are just network-connected thin clients for machine learning algorithms running in the cloud in remote data centers. But if there isn't a network connection because there isn't a need to connect to the cloud, the attack surface of a smart device can get a lot smaller. For me, myself, the main driver towards the edge and machine learning there, rather than in the cloud, is not technical. It's not about security, although it's going to help. It's moral and ethical. Privacy for users is easier to enforce if the architecture of your system doesn't require data to be centralized in the first place. Privacy is not really about privacy. It's about users making a choice about what they tell you about themselves. And the arrival of hardware designed to run machine learning models at vastly increased speed and inside relatively low power envelopes without the need to connect to the cloud has made edge-based computing that much more of a viable proposition for a lot of use cases that previously we've used cloud-connected devices to service. One of the things I did towards the end of the before times, pre-pandemic, was to take a look at exactly how much faster things have gotten. And I published a series of articles talking about both the new generation of custom ASIC designed to run machine learning models at the edge and comparing them to the current generation of SMB, single board computings. One of the things that stood out, and I think this was really one of the first things that came up, was the increase in inferencing speed between the TensorFlow benchmark and the results using TensorFlow Lite on boards like the Raspberry Pi. Running on the same hardware, TensorFlow Lite ran between 3 and 4 times faster. And that wasn't using a newfangled proprietary model. It was the same MobileNet model, but quantized. And while we might expect some reduction in accuracy due to that, and yes, there was some, it wasn't really significant. The sort of speed up was astonishing, and it really showed the power of quantization. In fact, the decrease in inferencing times by using TensorFlow Lite and quantization brought the Raspberry Pi 4 into direct head-to-head competition with the custom silicon from both NVIDIA and Intel that was available at the time. A normal off-the-shelf ARM chip doing machine learning inferencing just as fast and for a lot less money than custom silicon from big players. And for those of you that think better in graphs, including me, Here we have the inferencing time in milliseconds for the MobileNet V1 SSD 0.75 depth model, left-hand bars, and MobileNet V2 SSD model, right-hand bars, both trained on the Common Objects and Context COCO dataset. Standalone platforms are in green, while the single bars off to the right in blue are for the XOR AI2Go platform, and timings are for their proprietary binary weight models. That's the company that briefly appeared and then disappeared and got bought by Apple, and hopefully one day their stuff will once again appear publicly. All the other measurements are for the accelerator hardware attached to the Raspberry Pi 3 Model B in yellow or Raspberry Pi 4 Model B in red. And you can see that the Raspberry Pi levels are roughly on par with the accelerated ASIC, which is pretty astounding. And it's notable that the only platform to keep up with TensorFlow Lite was Google's Edge TPU, which also leans heavily on quantization. And the results really started me wondering whether we'd all gone ahead and optimized in hardware just a little too soon. Because if we can get that much software leverage out of software, out of quantization, then perhaps we need to wait till the software in the embedded edge space has matured enough so that we know what we're optimizing for. Because there is really an obsession in the machine learning community about accuracy. It's the yardstick by which everything is measured. And I think that comes from the academic background of quite a lot of people in the community. Personally, I would argue that the accuracy of a model isn't necessarily the only thing that should concern us, or rather you can't define the utility of a model by a single number or even a small group of these numbers. At the edge, other things matter more, or well, might matter more than a few points off the accuracy in a model. And performance like this does mean that we have to take a hard look at the last 10 years, a hard look at the mistakes we've made during the big data era and try to not replicate them again in the edge years. We do indeed have to do better than that. We need to make sure that privacy is designed into the architectures we're using, not just at the inferencing stage where we're taking trained models and deploying them in the real world, but all the way back when we're training them. Because models, once trained and deployed, hang around for a very long time in the real world. They don't get regularly updated. They do not get disposed of and replaced with new models. The first job I ever had as an adult, fresh out of my undergraduate, was at a now defunct defense contractor. There, amongst other things I can't talk about, I built neural network software for video compression. So to be clear, this was during the first, well, maybe it's the second time this stuff was trendy, back in the early 1990s, when machine learning was still called neural networks. Anyway, the compression software I built around the neural networks left rather specific artifacts in the video stream. And every so often, I still see those artifacts in video today in products by a certain large manufacturer who will remain nameless, who presumably picked up the IP of the defense contractor for a bargain price after it went bankrupt. Those networks, presumably now buried at the bottom of a software stack, wrapped inside a black box with "Here They Be Dragons" written on the outside, the documentation I left behind was that bad, are still around 30 years after I built them. Which makes accessibility to pre-trained models in what have colloquially become known as model zoos rather important. Because while you might draw an analogy between a trained model and a binary, and the data set and the model it was trained on and the source code, it turns out the data might not be as useful to you as the model. Taking a step back, I've argued in the past that the GPL, for instance, is now far less important today than it was 30 years ago, when we were fighting the first rounds in the war against proprietary software and vendor lock-in. 30 years is a long time in internet time, and things have changed a lot. Access to software these days is no longer difficult. Access to source code is relatively easy, even for the most part assumed. Although some people now argue that cloud computing is bringing us back into another war against vendor lock-in, that many services are effectively closed and proprietary, and even services that are based on open source carry proprietary extensions. This is an argument to support the GPL, in support of copyleft. And to an extent, I think they're right. We do have a problem with vendor lock-in in the cloud. But I think the cloud is a very different battle than the one we fought against proprietary software back in the 90s. The problem inherent with hosted services isn't the ability to replicate the service. Most people, most of the time, would be unable to do so, even if they were given the source. If you got a hard drive with the source for Google on it handed to you, you could not spin up Google. Instead, the problem itself is the data, our data. We should therefore possibly be more worried about data portability licenses than open source licenses, at least when it comes to the cloud. With machine learning, we're taking the next step. Maybe we're really interested in the availability of trained models rather than the data they were trained on. Because let's be real here, the secret behind this recent string of successes for machine learning isn't really the algorithms. The algorithms have moved on a whole bunch since the first time I played with them back in the 90s. But this stuff has been lurking in the background for decades, waiting for computing to catch up. Instead, the success of machine learning recently has relied heavily on the corpus of training data that companies like Google have managed to build up. And for the most part, these training data sets are the secret sauce and closely held by the companies and the people that have them. But those data sets have also grown so large that most people, even if they had them, couldn't store them or train new models based on them. But on the other hand, perhaps we can make use of their trained models and transfer learning to help solve our problems, which makes the provenance of that training data for the models a huge dilemma for those of us attempting to deploy machine learning models that are pre-trained. While not tinyML by any means, GitHub Copilot is an interesting example case. When GitHub announced Copilot back in June, the company said the algorithm had been trained on publicly available code posted to GitHub, and it said, training machine learning models on publicly available data is considered fair use across the machine learning community. But this isn't a legal question that's quite as settled as you'd imagine. Making data publicly available doesn't mean you can use it legally to train your model. There's no direct legal precedent in the US or the European Union or the UK that upholds publicly available data as fair use for training models. Another example is Imagenet. It's amongst the most influential of the big AI training data sets. The project has been instrumental in advancing computer vision and deep learning research, but it's made up of publicly available images that Imagenet creators do not own. If a court were to say that using this data isn't legal, that would have far-reaching effects on how we train models, and it isn't an inconceivable occurrence, if not in the States, and certainly in the European Union, where GDPR has proved it's taken a much more stringent stance on user privacy. Ethically, the use of data without anything except implicit permission from the originator has to be a gray area. And of course, there's also the issue of origination. This isn't something that's come up often at this point, as machine learning is, at least right now, mostly used to interpret the world rather than create new things in it. But for instance, what license is the code the GitHub Copilot writes releasable under? Since it has been tested in court, no judge has yet been forced to decide how extractive the technology is. And it's not impossible that a judge might well decide that the licenses applied to the code used to train the model might well propagate virally to the content that is created by the model, that it produces derivative works rather than original work. Which brings issues such as attribution for Creative Commons licenses and source code release for licenses like the GPL to the fore. What is the source code you'd have to release at that point? The model itself, your training code and pointers to the training data? It's extremely unclear. And using data harvested somewhat indiscriminately opens you to biases just as much as curating a data set, because the data set public does not mean it's free from bias. Questions around bias and ethics need to be addressed now, urgently, not because we aren't acknowledging them in the community, but because outside the community, they aren't yet evident. but they are going to be soon. Machine learning, and especially tinyML, designed as it is to be deployed into the real world in real situations and interact with real people, is now being commoditized. We should know we are the people doing it. It's no longer restricted to the community. Normal developers, rather than machine learning researchers, are starting to pick up and use the tools we've built. People that don't necessarily instinctively understand issues like biases. Because I'm sure everyone here will admit our models are inevitably biased. There may well be pre-existing biases inside your organization. These will range from broad cultural biases, biases inherent in your industry of business, and they're typically going to be replicated or even amplified by any model that you build. It's hard, if not impossible, to deal with these sorts of biases. More addressable are biases introduced by the way you frame a problem. Does the problem definition consciously or unconsciously discriminate? For instance, algorithms developed to help decide which patients needed extra medical care turned out to be more likely to recommend relatively healthy white patients over sicker Black patients in the United States. The algorithm sorted patients according to what they had previously paid in healthcare fees, meaning those who had traditionally incurred more costs got preferential treatment. And here's where the bias creeps in. When breaking down healthcare costs, the researchers found that healthcare system less inclined to give treatment to Black patients dealing with similar chronic illnesses compared to white patients. We talked about this earlier, but it's worth pointing out again. Now I'm talking about biases. Is there a bias found in the training data coming from sampling or collection issues? You do need to take a hard look at the provenance and profile of this training data and look at potential risk areas to see if there are imbalances or outliers that could lead to problems in a trained machine learning system. Model misuse may also be cause for concern and introduce biases. Is a model trained for one use case now being used in a different context? Or alternatively, has the world around the model changed? Has the model outlived its use? Models work fine one day and can return incorrect or biased results the next if the way the world works changes without the model itself being updated. And most machine learning models, especially tiny ones, are narrow by design and don't generalize well between use case changes. And most of the discussion I've seen around model biases is about public relations, as if the most important thing when using a biased model is not getting caught. And speaking of not getting caught, I talked earlier about security or lack of it when it comes to network connected devices. Machine learning, of course, has its own somewhat unique attack surface, adversarial attacks. Two stop signs. The left with real graffiti, something I think most of us would just think not as particularly suspicious. The right shows a stop sign with a physical perturbation, somewhat more obvious to a human, but it could be disguised as real graffiti. Those 4 stickers on the right-hand sign makes a machine vision network designed to control an autonomous car read that stop sign, still obviously a stop sign to us, the mere humans, as saying speed limit 45 miles per hour. Not only would the car not stop, it might instead speed up. You can launch similar adversarial attacks against face and voice recognition. And for instance, you can bypass Apple's Face ID liveness detection under some circumstances using a pair of glasses with tape over the lenses. Of course, when you think about it, the easy susceptibility of models to adversarial attack should not be entirely unexpected, because we made machine learning network models to look like us. A model is essentially a brain in the box, or at least what we thought was a brain back when the field was first considered. We've since learned that brains don't really work how we thought, but that's a whole different talk. Anyway, our own brains are susceptible to the same sort of adversarial attacks, like this rather bizarre dazzle camouflage from World War I battleships. Which brings us to an issue of trust. Most, perhaps all, Internet of Things architectures I've come across implement system-level trust. Actors in the system are assumed to be trustworthy and to abide by the rules of the encounter, so that protocols and mechanisms that regulate the system. Systems trust their own measurements, not necessarily when they're made, but once they're in the network and in the system. And if there's one thing I can definitively tell you from my physics background, you should never trust a single measurement of anything. In any case, I'm not a great fan of system-level trust, as it ignores the fact that in the real world, things break. It also ignores the possibility of maliciously injected data, and in the case of machine learning, adversarial attacks. And just because one actor in the system thinks it's trustworthy doesn't mean it actually is. Data can just be bad. Which brings us to reproducibility. Especially as machine learning moves out of this community and starts being deployed by non-specialist developers, then looking inside the black box may well become far more important. If you think that everyone using your models or training their own based on your algorithms will understand the intricacies and limitations of those models and architectures, then you've never copy and pasted code from Stack Overflow, have you? Legally, in fact, reproducibility might become necessary, especially in regulated industries and sectors. There are researchers working very hard right now to make NPL systems able to reason and then explain their reasoning afterwards. And there are some real-world tools that exist that look at quantitative input influences measurements, for instance. But right now, they're all aimed squarely at data scientists and machine learning researchers. The idea that even a year or two from now, machine learning models deployed at the edge will be built by data scientists or machine learning community is actually sort of laughable. Folks trained in statistics and how they interpret the outputs of the current generation of tools based on their own experience are not going to be the ones training and deploying models in most organizations. Right now, we have a precious moment in time when the world is once again changing, when all we have here are the only, and where the people here are the only ones that can build the new things with new technology, because we're the only ones that have the knowledge to do it. But we're stuck in the trenches day to day, and it's hard to see over the top of the problem that's right in front of you to the bigger picture. And if you do, it's easy to assume that there's someone else's problem. The bigger picture will take care of itself, that it will in fact fall out naturally from the technology. That didn't work for big data. 10 years of big data, 10 years of attempted technological fixes rather than cultural ones suggest that it isn't the best course of action, that we need to have the sense to build architectures that are harder to abuse, that preserve end user privilege and privacy. We have a moment we can grasp if we want to change how technology works. And I very much want you to all think about that and then go off and build things slightly differently. Thank you.
Amazing talk. That was super interesting. Thank you so much, Alasdair. That was really, really interesting. I find it is one of those fields that is growing very fast, like the whole tinyML space, and there are a lot of challenges that I think we tend to like not look at, right? And this was a sort of wake up call for me. I mean, these are things that we do look at, but sometimes like I think we're kind of still early when it comes to like having the right tools, the right solutions for solving these at a large scale, right? And I think one of the things that like you brought up.
I mean, I think that's exactly right. We tend to be very focused on the technology. We tend to be focused on the problems that are right in front of us, to improving the accuracy score of a model, or training it slightly faster, or getting faster inferencing, or like making model deployment easier. And I was there at the beginning of the big data era, and I was going to conferences. Remember when you could go to conferences? That was fun. And I was there at the conferences, and we were talking about the technology, and there was very little attention paid to the ethics and to the privacy, except in throwaway phrases at the beginning of talks or at the end of talks. And it would be nice this time to do it better, I think. We've had 10 years to see where ignoring these problems go, and it didn't work out that well.
Yeah, and I completely agree with your point of the fact that we're actually opening up to a lot more people developing models, right? Like I think compared to like what happened in the past, I mean, there was a lot of data scientists, but I would say the number of embedded engineers and developers across the board are way more than the number of data scientists we ever had, right? So because we're now opening up to all those developers, and we're giving them a chance to like create models, create solutions that are based on those models, we really have to like start thinking about how do we make it easier for them to like realize that their data are biased, that the data set are biased, and that their models are performing based on those biases, right? I think that's super interesting.
Most of the tutorials you see, if you're coming in as a non-specialist developer without much background in the field, except if you're a younger person, perhaps the 10 credit course you took as an undergraduate or something like that. If you come in without much background in the field, the tutorials you're going to go to, the places you're going to go are going to be very mechanical. You're going to be like this is a snippet of code, do this, do that, here, pull the data in, this is how you convert your data into tensors, this is how you drop it into a model. Here you've got a trained model and it recognizes your banana, that's great. But that doesn't teach them about how the data is represented by the model. A lot of the developers coming in won't have and will not be prepared to acquire the higher level of mathematics needed to really understand exactly what's going inside those networks. And they, quite frankly, these shouldn't be. That's not their specialism. They shouldn't be required to do so. The community should make it easier for those sorts of folks to be able to build things with the tools that we're creating and have some sort of warning, some sort of idea that they've done it wrong, and what they're getting out the back end is not what they really naively expect to get.
Yeah, I mean, completely agree. And I think, my only hope is that, as you said, like there is, this is a growing space and we are a big community. And my hope is that we can solve this together. I also do think, though, that there is one big difference when it comes to kind of embedded machine learning versus like big cloud stuff. And the difference is that stuff is the models and the solutions are usually very specific for a specific problem. So perhaps it's not as worrisome as it is on like big data. And but I still do believe that biases are something we should be very careful about, right? Because you never know how things.
Yeah, I mean, it depends exactly what the problem you're trying to solve is, right? There's the GDPR specific sections that protect people, citizens of the EU and the UK, at least for now, against machine-led decisions that could significantly affect their life. So, for instance, there's an ongoing bubble around gig workers, where Uber drivers, or it might be Lyft drivers, I can't remember, are having their accounts limited by the algorithm, and that's stopping them earning money, which is like an algorithm making a decision about someone's livelihood, and that's going to go to court, very obviously. But there are things that, like embedded machine learning, is going to make a difference. I mean, skin color is an obvious one, right? If your training data set does not have a representative sample of people, and you're doing face recognition or hand recognition, there was a case where I think it was a blow dryer for your hands didn't activate when darker skinned individuals put their hands under it, because the software running it didn't recognize that those were hands.
Yeah. Interesting. I mean,
so you can put human affecting biases into very primitive objects.
Yeah.
If the data you're putting in are wrong, or the way you've trained the network is wrong, or the question you were asking in the first place is wrong.
Yeah, agree. I mean, 100%. I think another point that I wanted to make, and then we'll take the questions. But another point that I wanted to make based on what you said, I think I completely agree with you that we shouldn't base our systems on black boxes that you can't look inside, right? I mean, I think there's two separate topics there. That one is like AI explainability, so being able to like know why a model is making it's taking a certain path or making certain decisions. And that's one, a whole field, and it's super interesting. And then the other aspect of that kind of is the transparency over rather than the explainability. And that's like being able to look inside, being able to look at the processes and tools that, each of the step that you kind of walk through to generate your model. I think these two are super important aspects. And I think hopefully by giving the ability to look inside, by giving the transparency, we're going to be able to at least alleviate some of these issues, right? Because people will be able to understand what models are, why the models are performing in a certain way, what they've been trained on, what they've been, what the features, what features have been extracted, right, in the process. Things like that, I think, are super important to just to even scratch the surface, right? Like, aside from solving the problem, I think you need that as a basis, right?
Yeah, I totally agree. And the two things you talked about are not necessarily in parallel. They're at times they can be quite orthogonal. But yes, both of them are very distinct reasons to look inside the model and look for that decision making. But yeah, it's absolutely, I think it's critical as machine learning spreads outside. Eventually it might not be as necessary, right? It's like, if we get to the point where models are more trusted, that we've got more experience, we're still very early days. I mean, as I said, I played with Cajonin neural nets back in the 1990s to do video compression, which are very different types of architectures than we're using now. And the way we looked at it is essentially as a black box. No one really understood. Like, you could explain what was happening, but you couldn't necessarily understand why certain weights were becoming like in a certain way. And like the tool chain has moved on, and there is more insight inside some of the networks, and in some places it's getting worse. I think it's like, as the deep learning networks get more complicated, those are pretty inexplicable, I think, to most people. I don't understand. Possibly some people do.
Cool. Well, Alasdair, thank you so much for the chat, as well as the presentation. We've got a bunch of questions, actually quite a few. So let's start taking some of them at least. So there's first question from Bill. It's not really a question, it's a thought. So I'll leave it there. Bill, maybe you can refine the question a little bit on the Q&A box. But we'll take the second one now. So from Alexander, do you see the future of ML training at the edge too, as well as on the cloud?
I think so. I mean, obviously, we have broken Moore's law, right? We can no longer rely on Moore's law to give us more and more compute power every year. We have to stop being greedy. And it's interesting to think that our children could go through their lives with computers that are not much faster than we are using today, unless some new novel architecture comes along and unbreaks Moore's law again. Because that hasn't been anyone in this virtual place's experience of how their life has gone. Computers have always been getting faster. But yes, I do see some training at the edge, refining possibly. I think building a basic model at the edge is a hard ask. If you have those sorts of resources available at the edge, it's not really the edge, it's more of a periphery. But yeah, I can see tweaking of models based on data coming in, trying to keep the model fresh.
Awesome. Cool. So the next one is a hard one. Get ready.
Okay.
No, I mean, I think it's coming from, actually, it's the same person, Alexander. So he's asking, based on your talk, right? You brought up a bunch of interesting points, and he's asking, how's the Raspberry Pi Foundation long-term, what are the Raspberry Pi Foundation long-term plans to address the problems which you mentioned today?
Okay, first of all, I don't work for Raspberry Pi Foundation. I work for Raspberry Pi, which is the trading arm. We're the people that design and build the actual hardware and distribute the software. So I cannot speak for the foundation because I do not work for them. And secondly, I will give you the Raspberry Pi answer to all of things which look into the forward is we do not speak about future products.
Perfect. The next one is, how do you protect privacy when you need to upload training data, for example, images to a service to create a tinyML model? How do you test a model to determine what its bias might be? So two questions. How do you protect the privacy of the data that you're uploading on a service? And how do you test a model to determine the bias?
They're both really good questions, and they don't really currently have answers, not good answers. How do you protect privacy? Well, as I said, privacy is not about keeping things private. Privacy is about giving users choice. And it's to a certain extent, we have to look at the way ethics have been implemented in other fields. So in medicine, for instance, ethics is about informed consent. And we have been traditionally very bad at that. The cookie pop-ups, please, you're consenting to cookies. It's horrible. It's absolutely horrible. No one thinks that we have done that well, right? If you want to take your consent away and not give people data, the little button is buried at 7 menus down, and it's the opposite thing than you would expect, and the wording's horrible, and it takes you 20 minutes it's unusably poor. It's a technological fix to avoid giving the users choice. It's not a cultural fix to actually allow them to have informed consent and choice. So don't do the thing, the cookie law, don't do that. Do something else, but give the users informed consent if you are taking data from them, their data.
So I can speak. Can I just plug in one thing about? So I speak for Edge Impulse. So we have a policy that says clearly that we're not allowed to look into people's data right now. Obviously, the data has to be in our repository in order for you to process, or in our cloud bucket in order for you to process it. But it's not being observed at all, right? So there is there is policies in place to ensure that doesn't happen. But again, that's I can speak to that as specifically. The second part of the question was, how do you test a model to determine what its bias might be? That's an interesting one.
It is an interesting one, and it speaks to how you train the model. It to some extent it speaks to how you train the model. There is a tendency for people to have a pile of data and to take a subset of the data and train the model from that, and then test it against the rest of the pile. And that assumes that the data you have taken from the pile is at right angles or orthogonal, is not constrained by the rest of the data in the pile, that it's not associated with it. So I guess the rule of thumb I would give is that try and, if, for instance, you're deploying a sensor into a certain place or a certain number of places, take your data in a slightly different environment, or take your data in a slightly different way so that it reflects the real world diversity of how the data is taken, not just what is in the data set. If you have a test sensor sitting on a lab bench taking data, that's going to be a very different environment and will bias your model to a bunch of sensors deployed into the real world, into real world conditions. So diversity, not just of data, but of training conditions, I guess.
Yeah, I completely agree with you. I think there isn't really a silver bullet, at least not one that I know, but I think it's all about really understanding that, having a good confidence that your data set is as wide as possible, as broad as possible, and really kind of testing on long data sets or really big data sets rather than like a small amount of data. For example, audio, a lot of times we tend to test or build models based on train models based on windows of data, right? Of audio. Yeah. And then when we test it in the real world, what happens is that you have you don't have a window, right? Like you're windowing over the audio sample. And what happens is that you might have some things that you never have in a cleaned data set, right? So things like that, I think there is a lot of difference between the real world data and the test data. So make sure that you do test on real world data at some point in your flow.
Yeah.
So good question. Actually, I want to say hi. Sandeep is online as well. Hi, Sandeep. Hi, Sandeep.
Oh, hey,
Great to have you here. He's got a question. How do you see EdgeML models being updated in the field? And so you kind of talked about this slightly earlier, but there's also another question connected to this that's also interesting is, will every device need radio communications to update the models, right? Like,
yeah, I mean, this is a tricky one because we know from the Internet of Things that people, if given the choice, will never, ever update anything. When was the last time you saw the little pop-up on your laptop screen that said, hey, please put this vital security update. This will require a reboot, and you hit cancel or postpone because you do not want your thing rebooted. That is just basic human nature. So I have two different answers to the question. The first is that in practice, I do not see models in the field being updated very often. This could be a problem. In theory, I don't know. Yes, if you're going to update your models, you need a radio connection. One of my devout hopes is that we can have more objects that don't have always on radios, that that don't have to connect back to the internet to do something smart. I think that's a huge win for privacy, for robustness even of smart objects, by having them not talk to a network all of the time, to be able to be offline and continue to do the smart thing. So opportunistic radio connections, perhaps, or periodic radio connections might be necessary to update the model. I mean, it depends on circumstances. Some things don't change very much, right? And maybe models trained to identify various things don't need to be updated, but some do. So I think it depends on circumstance. But in practice, I will guarantee you that once things go out in the field and sit there and start to live and do things, they will not be updated very often.
Scary, but true. Right, we're almost at the end, but there is a few more questions. Are you okay to stay another couple of minutes, take another few questions?
I can hang around.
Okay, so one question here that I think is interesting is it technically possible to introduce Trojan horses when training a model? So the model becomes poisoned and the inference behaves unexpectedly in certain situations?
Yes, in theory, absolutely. I think I might have seen a paper at some point where it was done. I can't remember exactly the details off the top of my head. I might be making that up. But in theory, it's entirely possible. It's essentially an adversarial attack during training rather than during inferencing. And the exact same things that make the inferencing adversarial attacks work would make it work in training. So essentially, you're skewing the weights on some of the neurons, like just a bit in one direction, so that as the model itself has a blind spot, or will preferentially pick one thing rather than the other. So yes, it's absolutely possible. I don't know whether it's been done in practice in the real world against real models. I would be fascinated to find out, but possibly we never will find out because the models are poisoned.
So there is a comment by Bill saying that that we're not thinking about the smart sensor that can be compromised nor be scheduled for downtime, and it would be a field disaster if that happens. Am I reading it correctly? It's in the comments. Smart sensors can be compromised. Yeah, basically, yeah. I think we're agreeing, right? Like we're saying it definitely can be a disaster if people don't update their models or don't update their firmware overall, right? And that's like the whole story of IoT. It's like you have to update your firmware. There was you mentioned a couple of actual hacks that happened in the past, right? Like you mentioned it earlier during the talk. So yeah, it's definitely a disaster. I think what Alasdair was trying to say is that there isn't really an easy way to get people to do it, right? So to update models and firmware and so on. I think we're still trying to figure out, I guess, how to enforce people. I think you mentioned, Alasdair, about the computer, how like it tells you to update, right? And sometimes you skip it. I remember there was a time when you could skip it for weeks. Now it doesn't allow you to skip it for more than a few days, right? Like so it's enforcing you to.
I have been skipping the updates on one of my Macs for the last year.
Okay, there you go. You managed.
I don't want to update that one. That one's stuck on the last revision of macOS that ran 32-bit applications. My main Mac, the one I'm on right now, has all of the security updates, folks. But like I have one particular Mac that doesn't leave my local network that is sufficiently old that it can still run 32-bit applications. And every day I click the Remind Me Tomorrow button on the please update your Mac.
Awesome. Okay, you managed to find a way then. Okay, just two questions that are kind of combined together. So there is a question around how do we get users to look inside their models or look inside their like flows? And there's another question around what tools generate interpretable models. Any insights?
I'm not 100% up to say or to recommend particular tools. I don't think there are a bunch around. I've not played extensively with all of the latest ones, so I would be hesitant to recommend a particular tool. I mean, maybe you can speak to that, Alexandra.
Yeah, I mean, I all I can say is that Edge Impulse. Obviously, I'm biased because talking about bias, I am biased because I work for Edge Impulse. But I can say that one of the cool things, I think this strategy to me to help people understand that they can look inside and that they should look inside is to allow them to do it, right? And to like actually walk them through how it's possible, what are the steps and what are the various implications of the choices that you make, and kind of like educate people along the journey. Because I think one of the worst things we can do as an ecosystem is to create tools that just do everything for you, right? Because then what happens is you're not inclined to look in the box, right? Like even if you're allowed, but you're not able to do it, right? Or sorry, you're not willing to do it because it's so much easier just to click yes and or whatever.
What we do have to do, of course, is make tools that do sane things by default, right?
Exactly.
I mean, they have to be conservative by default, not just sane. If the user knows what they're doing, they can skew the results themselves, and that's up to them. But the tools have to do conservative and sane things by default.
Oh, sorry, I was reading some comments, some interesting comments. There's an article that's been shared. But folks, I think we're getting at the end of definitely at the end of the hour. We passed that. So we should probably wrap up. And Alasdair, thank you so much for the time and the great talk.
Quite welcome.
I want to thank, the reason why, one of the good things about this community, tinyML, is that we have a lot of supporters, a lot of sponsors. So really kind of big thank you to all of the sponsors. I'll just go through them quickly. So ARM is the Hardware and Software Foundation for tinyML. Then there's DeepLight, and they make smaller and faster models. Then Edge Impulse, where I work, and we build an engineering tool for machine learning, for embedded machine learning. Then there is EMSA, Visual Sense, and they do Edge AI visual sensors. Then there is Green Waves that does a lot of different technology for the edge. Then GrooveT Inc., software development services for tinyML solutions, and HotG, distributed infrastructure for AI at the edge, Latent AI, adaptive AI for the intelligence edge, and then Maxim Integrated, a lot of interesting edge CPUs. Kixo AutoML, it's an AutoML tool for tinyML solutions. Qualcomm AI research, advancing AI research to make efficient AI ubiquitous. Reality AI adds advanced sensing to your product with tinyML. And then we've got Renesas that builds a lot of core technology, core CPUs for the edge. Seed, the IoT hardware enabler. tinyML, smart IoT sensors devices that are able to be trained with tinyML. SynSense, sensing inference hardware for ultra low power. Sentient, they do end-to-end deep learning solutions. So it's a hardware company. And then, as I mentioned at the beginning, there is an interesting talk tomorrow by Odin Shen from ARM on tinyML hardware and software co-design. So be sure to attend that. And with that, we can wrap up. It was great talk today from Alasdair Allan from the Raspberry Pi, and a lot of great questions, a lot of interesting questions and comments on the chat. So thank you all for joining, and thank you all for spending the time with us today.